In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 3, Yield Criteria, Part 5. Well, in this chapter, we presented the yield criteria function, and we said that we set the conditions for this yield to occur, and we determined what conditions the yield criteria should satisfy. And we reached some conclusions about the yield criteria, and criteria like Mises and Tresca were derived from our discussion. Now this figure, which is shown in here, is a projection of the stresses and stress axes, stress coordinates in the three-dimensional space into the pi plane. Okay, so this is the pi plane, sigma 1, sigma 2, sigma 3, the epsilon 1, the epsilon 2, the epsilon 3 are the stresses and strains projected onto the pi plane. And we said that when we project these into the pi plane, any scales, any vectors, any stress vectors, any stress values in the three-dimensional space, if we project it into the pi plane, we should multiply it by a scale factor of root 2 over 3, like that. R is equal to root 2 over 3 times y. And we determine different values in this figure for the yield criteria, Tresca and Mises. Okay. Also, we derive this parameter, which we call the load parameter, and we said that if we move 30 degrees here, 30 degrees, we could 0 to 30 degrees, we could get all the possible states of stress in the yield focus, okay, on here and in here. And we derived a relationship between x, y, and sigma 1, sigma 2, sigma 3, and also r theta, which is this, that is r, and that's theta. In here we can say that OB is equal to OA cos theta. Okay. OB is that length in this triangle is equal to OA cos theta. And OA is root 2 over 3 times y, because r is equal to that. Okay, the radius of the circle, of the yield of the Mises circle, is root 2 over 3 times y, because we said that if we multiply by this scale any values, we get the projections onto the pi plane, and that's what we have done in here. So if we substitute for OA in here, and obviously theta in here is 30 degrees, and we get OB equal to this expression, which becomes y over root 2. Okay, so now we understand how to derive these relationships and obtain these values on the pi plane. So that's for the Tresca, and that's for the Mises criteria on the in the pi plane. Right. Now, if we continue our discussion, we will get x is equal to y over root 2. That's r equal to x. That's in the x direction. And we had x equal to sigma 2 minus sigma 1 over root 2. So sigma from here obviously we have sigma 2 minus sigma 1 is equal to y, because we have root 2 here and there and they cancel out. And if we look at this picture, we will see that at different zones, we have 6 zones here. You know, every 60 degrees is one zone. We could say every 30 degrees because there is symmetry between along this line. But at different zones, we could have different values of stresses. For instance, sigma 2 greater than sigma 3 greater than sigma 1. If the stresses are like that, the values of the stresses are like that, then sigma 2 minus sigma 1 is equal to y. See, the biggest stress, the smallest stress. Okay, that's the middle one. That's for Tresca, you know, these lines. Okay, you can find out the equations of this line. So if the for the Tresca, usually we have it like this: the biggest, the maximum stress minus the minimum stress. So that is the yield criteria for Tresca. And we have this again. We derived the value for the Tresca yield criteria for this zone, which in this zone, if you look at it here, we got sigma 1, which is negative. We have sigma 2 and sigma 3. And here we say that sigma 2 is greater than sigma 3, greater than sigma 1. So sigma 1, I mean the biggest value and the smallest value could be positive and negative, obviously. So for other parts, other zones, we could also get the same, similar expressions. For instance, here again, if you look at it, sigma 1 is negative here, and sigma 3 is positive, and sigma 2. So sigma 3 greater than sigma 2 greater than sigma 1. So the biggest stress minus the smallest one, that's the yield criteria. Similarly, we could go around and get all the values. Here again, sigma 3 greater than sigma 1, sigma 2 is negative. Here, sigma 1 is greater than sigma 3 and sigma 2 is negative. And similarly in here, for all these zones, 6 zones as I said, we get all these values for the stresses. In fact, these lines and these arcs determine the yield surface. Okay, you can obtain these equations very simply, as I showed you before. Now we could project the three-dimensional space into the pipeline, so we get 3 axes. But if one of the stresses is 0, for instance here sigma 1 and sigma 2, we have normalized it, divided by y, they are normalized, dimensionless, and sigma 3 is equal to 0, so we have only 2 axes. So we say this is a two-dimensional stress space, and we could work out how the values of stresses and yield, von Mises yield criteria and the Tresca yield criteria are. As you can see, von Mises has become an ellipse, and the hexagon for Tresca has changed shape in such a way that it's not, it doesn't have equal lengths either. So why does it become ellipse? Because we have only 2 perpendicular axes, and it's like before we projected the yield surface onto the yield locus onto the pipeline, and pipeline was perpendicular to that cylinder, The cylinder was perpendicular to the pipeline. In fact, we cut the cylinder. If I show you here, we cut the cylinder perpendicular to its central axis. That's the central axis, perpendicular to the plane of this monitor, and we got these circles and hexagons, which is equal angle and equal length hexagon. Okay. Now, if the plane that we cut the cylinder, if it is not perpendicular to the axis, to its central axis, then what happens is that the plane that we cut the cylinder makes an angle with the central axis. So if we look at the cut section, we will see an ellipse. Okay. Now here, because we have omitted one of the axis, sigma 3 is 0, so the plane looks like an ellipse, and we want to know how things are as it stands. Well, for the three-dimensional case, we had this relationship. So if we put sigma 3 0 here, we get this relationship, and we get this. If we omit 2, cancel out this 2, and this is obviously sigma 1 minus sigma 2 equal to y, and for sigma 1 greater than sigma 2, we have this relationship, and these are the minor and major axes of the ellipse, which are 2y root 2 over 3 and 2y root 2. Okay, so if you remember, these were before like that is root 2 over 3, y and y divided by root 2 were the radius of the hexagon and the radius of the mesocircle. So now that it has become an ellipse, this has become the minor axis and this has become the major axis with these values. Okay, and here again I have for the mesos, I have shown how the stresses change. Is just a repeat of what I said in 2 slides before. It's just for remind you if we have a stress element, what are the stresses? For instance, here before I put sigma 1, 2 and 3, here we have put sigma x, sigma y, sigma z. So here you see that sigma x and sigma y in this region are both positive. Here like that, here one negative, one positive, and so on. Okay, so obviously here is different from the slide that I showed you before, because here is two-dimensional space, and for these cases we have sigma y divided sigma y greater than sigma x greater than 0, both positive, and sigma y is equal to y, and here sigma x greater than sigma y greater than 0, sigma x is equal to y, and so on and so forth for the all conditions all around this Tresca hexagon. Right, now we want to know if we could prove these criteria, because we use the mathematical equations as we set some conditions, like isotropic material, Batchinger effect is omitted, and hydrostatic component of stress does not have any influence on the yield criteria. With these conditions and with our formulations for the deviatoric stresses and so on, we obtain some mathematical equations, and we also interpreted those mathematical equations with the geometrical representations, and we got some understanding of the yield criteria. Now we want to prove them. To prove them, usually we must carry out experiments. I mean, if you have a theory, if you have a mathematical relationship, then you must carry out some experiments and obtain experimental data and compare it with the theoretical data and see whether they are correct or not. Now, in order to do the experiments, obviously from many years ago, for instance 1931, Taylor and Queenie did an experiment and published a paper, The Plastic Distortion of Metals. If you could obtain these papers and study them, it's very good. I don't have time to search for you and obtain it, but I'm sure if you go and search in the internet, probably you can get hold of these papers. If you got it, please put it in the group so that everybody can use it. Anyway, these experiments of Taylor and Queenie was on a tube like this. This is a tube, cylindrical tube, and what they did, they put it under tension and torsion. Okay, torsion and tension, combined torsion and tension. Some people pressurized this cylinder and put it under torsion and bending and so on. So why do we put it under combined loading? Because we want to have shear and normal stresses and stresses applied in all directions. Okay, so that's why we put this combined stresses. As I said, we could put internal pressure and bending, internal pressure and torsion, compression and torsion, compression and bending, all sorts of combined loading we could apply and get the results. What results do we get? As explained here, they carried out a series of experiments on, this is a thin-walled cylinder made of copper and steel, and obviously we know from the strengths of material that under this combined loading we have normal stress and torsion, and that's the stress element. So these are the only stresses applied at this element, and the principal stresses become like that. Okay, so sigma 1 is half sigma plus a quarter sigma squared, 2 squared, and so on, and sigma 3 here is negligible, so we assume that it's 0. Okay, so if we have this torsion and tension, then we could get these values and put it there and get the principal stresses. So we must measure. It's like a tension test. As you apply the tension and as you apply the torsion, you start from 0 and you apply different values of torsion and tension. Obviously you would have to do many experiments, not just one experiment. For instance, you can apply a certain value of tension and then start increasing the torsion and measure the values, and then you can apply a certain torsion and increase the tension from 0 to some certain values, and you can change the constant values of tension and torsion. So as you can see, you can do tens of experiments, and out of these you obtain the values and put it in here to get the principal stresses. Okay, so once you get the principal stresses, then we could get sigma 1 minus sigma 2 and put it in this relationship, which was for the yield criteria, and you get this value 2 sigma squared plus 3 tau squared, and therefore you get a quarter of sigma squared plus tau squared equal to y squared over 2. So what we do is that we use the Tresca and Mises yield criteria, and then if we put these values, we will get different values for the points y. In fact, you can see here that we have an equation for ellipse again for Tresca, because in fact that hexagon is so stretched that it has become an ellipse. And also for the Mises criteria we have another ellipse, and that's how they look like. Okay, the Tresca criteria and the Mises criteria, these values are a bit different, that's why we get these two shapes like that. And that's what we get. You see, this is the theoretical value which obtained before. Tresca also we get this, and then these points are those experiments that I said we carried out. But what we have done in the experiment is that we have applied a certain amount of tension, and then we added some torsion to it, increased the torsion so that the cylinder reaches its yield point. Okay, when it is yielded, we notice the value of the torsion, and we have the value of tension as well. Therefore we have tau and sigma on the yield point, so we find one of these points. Then we change the combination of the loading. For instance, we increase the tension and then apply the torsion and increase it until we reach another point of yielding. Okay, so as you can see here, these are the axes tau and sigma, and so we have to measure tau and sigma, or in fact obtain tau and sigma and put it in the equations to get this yield point. And we have these points which are at the yield point where sigma is 0, and this is y where tau is 0, and these are the points of yielding. And so this is the theoretical one, this is the theoretical one, and these are the points experimental ones. So you can see the experimental points are between Tresca and Mises, and generally we say that Tresca is very conservative and Mises is more realistic. So that's why the points are situated here. It very much depends on the material as well. As we have said here, this was for copper and similar materials. But if you have, for instance, cast iron, that would be much different. Maybe you get it here, maybe you get it there. So the behavior of the material and the composition of the material very much determines the yield criteria that we must use, but generally this is the case. Now these are the Mises and Tresca that we have drawn here. Mises was an ellipse, Tresca here is an ellipse, because we have this combined loading, and we get these equations. Okay, now the other test results have been obtained like this. As you can see, we have here Mises, Tresca, and another yield. This square is another yield criteria which is called maximum normal stress yield criteria. And as you can see, for cast iron we have some points in here which the maximum normal stress criteria accommodates that. Maximum normal stress, as the name implies, the yield criteria is based on the maximum normal stress. If the maximum normal stress reaches a value, then it yields. Okay, so here it does not yield, it yields here. But when we have tension, you see in compression, cast irons and similar materials which have low ductility and very brittle, and they are very brittle, they are good in compression, you see here and there, but in tension they are weak. So in these plus signs, you see, are inside the Tresca and Mises criteria. So that's the picture for different material, aluminum, copper, steel. You can see these Tresca and Mises are good for them, but for cast iron they are not good. This maximum normal stress is good. Another thing you can see here between copper, aluminum and steel, you can see that small circle, we have it somewhere here inside the hexagon and inside the Tresca and Mises criteria, but the copper and aluminum almost on the line criteria, on the yield criteria in here, and the yield locus, and because they are FCC materials, this copper and aluminum, and they have high ductility, that's why this Mises is very good for high ductility material. But for brittle material it's no good. You must use maximum normal stress. And for steel, depending what kind of steel it is, because we have many thousands of steels, and but it's not as good as copper and aluminum because it's BCC structure. These are FCC structures. So that's why we get some points, you see, some points on the yield loci, some points inside the yield locus, and but we have many points also in here as well. Depending on the what values of sigma 1 and sigma 2 we have, it may be inside. Anyway, we use the factor of safety for this kind of behavior, to accommodate for this kind of behavior as well. Here we have shown some other materials like nickel, chrome, molybdenum steel. This is a high alloy steel. This is a 1023 steel. This is a simple carbon steel. It has 0.23 percentage of carbon. This is steel, simple carbon steels. And this is aluminum T4 series 2024, and this is another aluminum, cast aluminum. So you can see that for a gray cast iron as well, gray cast iron obviously is ductile and it's brittle, and we have this maximum normal criteria. But for nickel chrome, you can see that it's almost on the edges of the yield criteria. For simple carbon steel also it agrees with the yield criteria. Some points may not. And as you can see, when the sigma 2 to sigma 1, the ratio becomes smaller, higher. Sigma 2 to sigma 1 becomes higher at these points. Sigma 1 is smaller, sigma 2 is higher. So it does not agree with the yield criteria, but at these points it completely agrees with the yield criteria. So we have shown here different experimental results for different materials, so that you get a picture about the yield criteria in real practice.